Dobry din, and I'm afraid that's the extent of my Russian, so the rest is going to be in English. Good afternoon. My name's Rob McNeil. I'm from Matthews Daniel from our London office, and today I'm going to be talking about some trends that we've picked up in power claims. I'm going to use a couple of examples from Europe and the Middle East. Obviously, different regions to Russia, but some trends which may in the future be brought across to the Russian market, and potentially some stuff to look out for. So there's a whole range of factors or drivers that are influencing claims in traditional power. We've put just a few up here. The shift into renewables, different technologies, fuel supply issues, aging infrastructure, a change in business models, energy policies in different regions, and then investment, just to name a few. And as you may guess, quite a few of these are interlinked, and trends kind of pick up on a few of these issues. The two that we've decided to, or I've decided to discuss with a couple of case studies are firstly the fact that renewables are affecting the grid dynamic, particularly in Europe, but also in other regions, and this is leading to claims in older equipment on traditional power plants, which were originally designed for base loading, and I'll explain a bit more about that when we get onto it. The second issue is that the first power purchase agreements or power and water purchase agreements, which have been rolled out in the Middle East, are beginning to come to an end, and we're seeing a whole host of claims associated with that kind of situation. So how are renewables affecting the grid? I should probably mention or pick up on a comment I made at the start. In Russia, obviously, if we exclude hydro, the penetration of renewables is still quite low, but with a big renewable resource, particularly in solar and wind, that's obviously likely to increase. So in Europe, like we said, a lot of the traditional equipment, traditional power equipment, gas turbines and steam turbines are designed for a base load operation. That means that they are running quite consistently. They're not being ramped up and ramped down and shut off and shut down and started again. The conditions are quite consistent. That was how they were designed, but as we're seeing more and more renewables come onto the grid, firstly, often the renewables are prioritised over traditional power sources, and they're more flexible. They're able to turn on and off a lot quicker or more easily without putting stress on the equipment. So to remain competitive, the operators of traditional power, gas and coal, for example, are having to try and keep up with this and turn their equipment on and off a lot more frequently, which is creating a lot more stress on the system, on the infrastructure, and we're seeing claims, a high number of claims associated with that. So this is resulting in the usual discussions around policy cover, what the real cause was, whether it's an operational thing or some other thing. Prior information, i.e., what did reinsurers or insurers know exactly about the equipment at the time and the operation at the time, and then obviously the resultant damage, whether that's going to be a wear and tear issue or whether it's something that will trigger the policy. So the main point on this diagram here, or this slide, is a diagram, and I just wanted to explain for those of you who aren't familiar with a traditional power combined cycle system. On the top there you have a gas turbine which is burning gas to produce power. Recovered from that is a lot of the heat which would otherwise be flared off. Recovered from that is the heat, which goes into the heat recovery steam generator, which, as you can probably guess from those words, generates steam, which then powers the steam turbine. It's introduced to the steam turbine at various stages. You've got the high pressure part of the rotor, the intermediate pressure section, which is closely linked, and then the low pressure part of the turbine. So that's a bit of background, which will hopefully prepare you for the case study, which I'll now try to explain. So this was a case in Europe where a major overhaul had been conducted in May 2018, so fairly recently. I should say that the claim was shortly after. The rotor was removed, and an inspection and a non-destructive testing course was followed, and no damage was. I apologise. And a crack was discovered approximately midway through the HP IP turbine. The crack went all the way around the rotor, so it was significant damage, and it was located at the bottom of a groove in and around the point where high pressure or hot steam is introduced. Here's some pictures of the damage. On the left is in situ, and then on the right you can see drilled down to determine the depth of the crack. As we point out in the words, that goes down to 9 millimeters, so not too deep, and in this case didn't mean a complete write-off of the rotor, but obviously needed to be repaired. So, like we were saying before, some of the stresses that come on the infrastructure through starting up and shutting down more frequently can be categorized as low cycle fatigue stresses. And these come about basically because you're heating up the rotor, which is a solid lump of steel generally. On older units, maybe it's hollow on more recent ones, but generally it's a cold piece of steel which you're heating up quite quickly, and that leads to, on startup, the exterior of the rotor being hot, but then the interior being cold, and then the opposite case on shutdown, where the interior of the rotor stays hot whilst the exterior cools down a lot quicker. And that difference in temperature creates stress, and then that obviously leads to, in some cases, cracking, and then you end up with a situation like this one. So, just to reiterate, this is something which the operator is having to kind of undergo just to keep up with the market. So they say they're having to turn their machine on and off again quite a lot of times, and this is the kind of stress that we see. So I'll start with a graph at the bottom. This shows over time the startup procedure on a turbine, on the steam turbine, and that means, as you can see on the blue section, that we've termed that the speed section. You're basically increasing the speed on the rotor, spinning it faster and faster until you get to a point where you wait. You let the temperature of the rotor become more uniform, so the interior catches up with the exterior in terms of heat. And then you increase the speed again before you attempt to put some load on, i.e. start generating power. So essentially you're undergoing this procedure a lot more frequently, and in some cases operators to keep up with demands, they're shortening those dwell times, so there's essentially less time for the rotor to heat through, to soak through completely, and that's just increasing the stresses. Some other factors in this case were, the first point is true of any, in that the gas turbine, the load on the gas turbine dictates how much steam is generated and the flow of steam and the temperature. In this case, the rotor temperature wasn't measured, it was calculated or modelled, and obviously that can lead to some inaccuracy. There was no automatic control system in place, and like I just mentioned, the OEM revised the startup procedure quite recently as a commercial driver to keep up with the market, essentially saying that you could shorten those dwell times and push the machine a lot harder. We also found out that the cold starts weren't complied with in recent times, so essentially the machine was being run a lot harder. Those dwell times were even shorter, and the stress was even more. So, claim was presented in terms of a defective design, but is that really true? The OEM indicated that originally the design and procedure prior to the revamp in 2015 was fit for purpose for base loading, but then cyclical, which is this start up and stop operation, wasn't going to be appropriate. So there's your first kind of issue. However, the material was in line with its design criteria at the time, and everything creep deterioration was to be expected. So, some conclusions, or probably some questions. The crack was formed through this low cycle thermal fatigue and creep, and then that was exacerbated by high cycle fatigue. That's a different issue. That's to do with running the machine a lot and towards the end of its life. But the main driver was this low cycle fatigue of starting and stopping. The rotor was machined, the damage, this crack was machined out. You can see in the green diagram at the bottom there, the original on the left profile, and then the repaired profile on the right. So essentially they improved the profile, they made the rotor a lot more resistant to this kind of issue, and you could say they probably gained an improvement. The plant configuration and rotor geometry was, as we said, not suitable for the present operating regime, and therefore they've managed to put in this new machined profile and ended up with something which is more suitable. And like we said, there was also evidence of non-compliance with the startup procedure. So there are a whole host of issues around this claim, which I can only say it's resulted in a negotiated settlement, and that's probably indicative of the way that the power market is, in that probably a few years ago you might have seen it being paid, but the market's generally being a bit harder these days, and there's some pushback. But that said, something is looking like, or has still been paid. The other issue, and I use the example of the Middle East, is to do with power purchase agreements, and this is essentially a sort of a take-or-pay agreement or a concession whereby a power plant is sold to an operator, owner, and then power availability is paid for by the off-taker, in most cases in the Middle East, the government. And this is probably a likely kind of contractual setup for how renewables will be come onto the market in Russia, probably privately developed and then with a PPA onto the grid. So a lot of these things in the Middle East were set up about 20 to 25 years ago, and therefore it's coming to the end of those in the early 2000s, and it's coming to the end of those agreements. And essentially the operators want to sort of minimise any further investment at this stage, because they've got an asset which has only a couple of years, say, yet to generate power, and therefore they're trying to really eke out the last bit of use of these things. Another important point, and touching on that, is that the OEM, for example, GE or Siemens or whoever has provided the turbines or units, often issue TILs or technical information letters, and they basically say that through their fleet maintenance, they've picked up some potential issues, and might be some modifications required to the operational procedure or physical modifications that are required to further operate the pieces of equipment. So again, if you're to comply with those TILs, then that's one thing, but if you're not to comply with them and to rather defer that investment or completely ignore that investment, who's kind of taking that risk? And then ultimately, when the contract, the PPA comes to the end, what is the agreement? Do they sell the infrastructure equipment back to the government or to somebody else? Or do they enter into a new power purchase agreement? Nothing is certain, so these are all just questions and factors. So in this particular example that I'll take you through now, there are various gas turbines, 4 of them installed in 1984. That was operated by the government up until 2000, when the operator-owner purchased the power plant under a power purchase agreement. That has then run for the best part of those 20 years, and we're now nearing the end of that. Recently there was a major inspection on this particular unit that we're going to discuss. The unit had operated for 195,000 hours, and I should add that about 200,000 is the design life, so it's approaching that. Importantly, a couple of TILs or technical information letters had been issued by the OEM, in this case GE, General Electric. One was issued fairly recently, and that was to do with the compressor aft stub shaft impeller. And that basically said for safety requirements you needed to monitor the unit more carefully, and at the next opportunity discuss with GE some possible physical modifications that might be required. An older TIL that was issued was to do with alignment of the unit, and that was to limit stress on the unit. So very briefly, this is the unit in question, and the aft stub shaft is basically at the end of the rotor, and that's basically what incurred the damage, which was a very, you can barely see it on this picture, but this is a boroscopic picture. It's not an easy thing to inspect. A very small hairline crack in this aft stub shaft. And that, like we said, had been run for 97 approximately % of its life, so it was really pushing the end of its life. So in this particular case, the insured had elected not to apply either of the TILs, and reasons given, among others, were that they didn't see that the TIL was applicable. They didn't know particular where, or there weren't signs that these things had to be implemented. But often a TIL will specify the urgency and whether it's an optional thing or something that is completely necessary. Then obviously there's the issues of the cause. Was this just a slow developing crack, or was this something which was triggered by a sudden and unforeseen event, and then also how the knowledge of those TILs and the fact that the TILs mentioned that there could be an issue with these components, does that raise an issue of foreseeability, or essentially did the insured know that this was likely to be the result? Then obviously what came into it were the exclusions, particularly focusing on wear and tear, and whether this was just a normal upkeep issue or whether this could be deemed a sudden event which should therefore trigger the policy. I'm afraid I can't really answer many of those things because it's like I said, like the first one, it's an ongoing thing, and it's probably going to end in a negotiated situation. So some takeaway points from both cases are the fact that renewables are obviously changing the dynamic of the grid, and that may in the future, as renewables penetrate more into the Russian market, be a case. And then operators of traditional power are having to change their model of operation to keep up with this change. They're essentially doing this, the OEMs are signing off this new way of operating, but really whose commercial expense is this? If claims continue to be paid, then it seems like insurers are footing the bill. But that probably can't be right. Secondly, that plants, particularly in the Middle East, are coming to the end of these power purchase agreements, and we're seeing more claims associated with that. But essentially, if the machine is at the end of its life and it hasn't undergone a life extension, should this really be something that the insurers are picking the bill up for? And then finally, like I said at the start, what happens to these plants at the end of these agreements, which obviously dictates the way in which they operate them. Are they going to sell them, or are they going to enter into a new PPA? Like I said, unfortunately not many answers, but just lots of questions. But hopefully some important points that may affect the Russian power market in the future. Thanks very much.